Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to do something just a little bit different. I have a radio from the late 30s era, and what we're going to do is just replace the components that absolutely need to be replaced under the chassis. So we're just going to replace the components that are stopping the radio from working, just the failure points. So what I'm going to do is bring the radio up slowly on a current-limited isolation transformer and variac supply, just to make sure everything is nice and stable. And after that point, we'll start the diagnosis and troubleshooting procedure together. So it should be a lot of fun. Let's get started. Here's the radio that we're going to diagnose and get working today. So one by one, we'll replace all the components that's stopping this thing from working. So we'll trace down all the faulty components and slowly bring this thing back to life. And we'll see just how many components we have to replace to actually make this thing work. Now, I have noticed that somebody has been in here at some time and they've replaced the line cord. I have a schematic for this thing, and I'm pretty sure I know why they replaced that line cord, because some people probably got a pretty good shock off of this thing over time, and I'll show you exactly why. The build of this radio is just a little bit different than All-American 5 and All-American 6 radios, to the point to where they've actually tied one part of the line cord directly to the chassis, and it's a direct wire right inside, right through the switch, directly to the chassis. So if you were to plug this thing in backwards with the original non-polarized cord, the chassis itself would be live, with 120 right on it. And of course, having 120 on it, if you were to, come across that, touch just the chassis of this thing, that would be, I guess you could say, a very enlightening experience. Definitely nothing that you would ever want to come across. So we'll take a look at that here as well. So what I'll do is I'll turn the radio around and we'll take a look at the backside here in just a moment. It looks like the dial moves, so there's no problems with the dial. The on-off switch clicks and it feels pretty smooth. Now, there are two bands on this radio. There's a broadcast band, and on the bottom, it looks like it goes from the top end of the broadcast band through the 160 meter band, right to the top end of the 80 meter, 75 meter band, right up to 4 megacycles, or 4 megahertz in today's speak. So it has a bit of a short wave area in it, and it also has a broadcast band. So when we're testing it, we'll just use a broadcast band because that's the most used one, and there's going to be quite a few active stations on the broadcast band around here, so that'll help us troubleshoot this. So what we want to do is we want to troubleshoot this just the easiest way possible. We want to see if we can get this thing working with a minimal amount of test equipment. And I'll show you multiple ways of finding the problem. We'll use different pieces of test gear, and we'll work our way to the problem with different pieces of gear. So I'll get the radio turned around, we'll take a look at the backside, see what we're up against there, and I'll show you that line cord, and then we'll take the thing apart and bring the thing up very slowly on a variac with current limiting. So whenever you get a radio like this, you never want to directly plug it into anything, especially of this age, because the capacitors inside, they go bad, they short out, and then what happens is you plug the thing and turn it on, and then you destroy a tube. So the tubes are getting kind of pricey for these older radios now and a little bit harder to find, so you don't want to take that chance. And that's why I'm putting this on a current-limited isolation transformer and variac supply, because again, one end of the line cord is tied to the chassis, so I want to be as safe as possible. Here's a closer look at the back side of the radio, and one of the things that I immediately noticed is somebody's name is written right on the IF transformer here. Now, this was common way back when the person brought this thing into the repair shop. The owner of the repair shop would usually write their name on the chassis. So they'd write the owner's name on the chassis, especially if there was more than one of these radios in there. So that way the actual owner of the radio got their radio back instead of, say, maybe a radio that looks like it. So it was really common back then to see this. And it's so clean still, nobody's taken it off, which is kind of nice. Now, obviously, as mentioned earlier, this has been in, so somebody's been inside this thing at some time because they've replaced the line cord with a polarized line cord. Now, I have the schematic for this thing, and replacing this with a polarized line cord without rewiring a portion of this radio doesn't make it all that much more safe. And I'll explain that here when we take a look at the schematic. So oddly enough, if they've attached the line cord correctly, when the radio is on, so when the switch is turned on, it's a lot safer than when it's turned off. Kind of interesting. So I'll explain why this is here in just a little bit. So keep in mind, way back in the day, polarized line cords were not a thing. So you could plug your cord in this way, or you could twist it around and plug it in this way. It could go in either way, which gives you a 50-50 chance of putting the hot side of your line directly on the chassis, which makes this thing pretty dangerous. So there are ways to make these radios a whole lot safer, and I'll talk about that again as we start looking at the schematic here. So we can see that somebody has replaced the antenna line with some form of, it looks like a piece of line cord. It might actually even be a piece of the original line cord. I would think that this maybe has a cloth line cord on it when it was original. So this just might be patched in there. So we'll find this all out together. So I've only taken a look at the schematic. We together are going to discover what is wrong with this radio. You know at this point as much as I know about this radio, other than me just having a quick peek at the schematic. So it should be interesting to look under the chassis and see what's actually been done, whether they've replaced any components with this line cord or whatever. Whatever it takes, we'll get this thing working piece by piece. So we'll replace only the components that are necessary to make this radio operate. So we'll troubleshoot this thing. Maybe we only have to replace one component, maybe two, maybe five in order to make this thing run. We'll find out. Contrary to popular belief, usually the tubes are the most dependable part of the radio. A lot of people think that whenever something goes wrong with a radio like this, first of all, a tube is dead. Actually, usually not. Usually it's something underneath the chassis. The tubes are usually very strong. So again, we'll find this out together. Now, this radio was around before the standardized All-American 5 and All-American 6 style tube radios were out. This is 1937 or about is when this radio was made. Now, in those years, they used tubes with filament voltages that don't add up to the standard line voltage. Okay, so in the All-American 5 and All-American 6 radios, if you add up all the filament voltages, they would add up very close to, the standard line voltage. Well, since this is going to be low, so if we add all of these filaments up, it's going to be quite low. It's going to be way lower than, say, 120, 115 volts, maybe even 110. So what they did way back when is they installed a ballast tube, and this really is just acting as a big resistor, making up for all that filament voltage that's missing because this is shy quite a bit. So in other words, okay, so what happens is way back when, the Christmas light strings that you used to buy from the store, all the Christmas lights were attached in series. Okay, so if one filament burnt out in, say you had a Christmas light string with 20 lights in it, okay, and one light bulb burnt out, the whole string goes out. It's not like the modern ones where they have that little wire in the bottom that shorts the burnt out bulb. Back in the day, it wasn't that easy. All the lights would go out, so you'd have 20 light bulbs to test out to see if, which one is dead, so you could make your string light up again, okay? Well, this is set up in much the same way. All the filaments in here are attached in series, so if one of the filaments in one of these tubes burns out, all of the tubes go out. So the next step would be to go to your local drugstore. Yes, the drugstore. So what would happen is most all drugstores, they had a tube tester in them, and you brought all the tubes from your radio to the drugstore. You would take the tubes and test each individual tube. So you'd have to set the tube tester up for each individual tube. Test that tube. If it works, you put it back in the bag, and then you go on to the next tube, and you keep testing all of the vacuum tubes until you find the one with the open filament. So just say your radio has 6 tubes in it, all right, and you tested all 5, and you're down to your last tube, and finally you find out, aha, this is the one with the open filament. You would call the owner of the drugstore. He would come over, and underneath the tube tester, they had a little lockup area. They would open up the lockup area and say the dead tube was a 6 Delta 6 or 6D6, okay? He would look through the stock. Oh, here's a 6D6. You would pay for that tube. You would bring the tube home, plug it into the radio and into the area that had that dead tube, and your radio works again. You know, putting all the rest of the tubes in, of course. It was very common for radio owners and even television owners way back when to repair their own televisions and radios. It was just a standard thing that people knew how to do way back when. Kind of interesting. So, of course, nowadays everything is solid state and there's no vacuum tubes in it and nothing's hooked in series like that. So, usually when something goes bad, the component has to be desoldered. But they made it easy. You could just pull the tubes out of the socket. So you say this was the bad tube. All right, so I'm just going to rock this gently. You never want to pull straight up like this and then, pull a lot of force, because what you're going to end up doing is the socket's going to let go of the tube and you're going to smash the tube into the top side of the radio. So here, as you can see, this is one of the tubes. This is the rectifier tube right here, right? And you just take this out and you would head off to your local drugstore with all the rest of them, plug it in, and test the tube out. And that was a very common thing to do way back when. So, again, all the tube filaments in here do not add up to 120 or 110, 115 volts, anything like that. So they put this large resistor tube in here to make up for that missing filament voltage. And as you can see, this one here, it has seen quite a tough life. It looks like there's almost rust inside the bulb. So hopefully the ballast tube, this is known as a ballast tube, it still works. If it doesn't, no big deal. We'll put a bunch of resistors in there and get the rest of the string working so we can continue troubleshooting this thing. But hopefully it does work. That would be nice. So now recognizing these tubes is really simple just by the way that they're put in. I should say recognizing their function, okay? So a ballast tube has filaments that are just strung up and down like this inside. So this, again, is just acting as a big resistor to make up for, say, the missing filaments, okay? So very easy to recognize that. This is a ballast. When we look inside here, we see two sections in here, and we see two cathodes with the filaments poking up out of the center of the tube there. So what is this? Simply, it's just two diodes inside of one tube. So this is the rectifier tube. So that's taking the line, all right, and it's rectifying that, and we get the correct voltage for the rest of the tubes in here, and it's rectified, so it's direct current. And then underneath the chassis, we have some filters to filter that off, so it's nice, clean, direct current for our radio. So if we wanted to, if we put a resistor across the filaments of this tube so that, we still have a series connection in here, we could replace both of those diodes with something as simple as a 1N4007. A teeny little diode would replace this big tube. And of course, we would need the resistor to make up for the missing filaments again. So rectifier tube right here. So taking the line, changing the line to DC for all the rest of the tubes. Okay, aside from this is the resistor that's in series with all of them. Now, they usually place the oscillator modulator or oscillator mixer, depending on who's designed it and how they've classified it, right close to the tuning capacitor. This is the tuning capacitor here, and there's two sections on that tuning capacitor, and they're ganged together. So that means that both sections move, they're in conjunction with each other, so they're the same. One portion of this capacitor tunes the oscillator, and the other portion is in making an attempt to try to tune the antenna. Okay, so the long wire or whatever type of antenna, it's going to try and tune that so that you get maximum sensitivity out of this radio. So oscillator and mixer or modulator. Now the IF amplifier tube is very easy to spot because 99% of the time it sits between the IF transformers. IF transformer, IF transformer. IF amplifier tube. Pretty simple. Just that easy. So this is the IF amp. And then after that, we need to detect and we also need to amplify that signal. So the next one down the string would be the detector and audio amplifier tube, and that would be this one right here. So you can see the path already is going this way. And the only tube left is the audio output tube, the tube that drives the audio output transformer, which drives the speaker, and that would be that one way back in the corner over there, like so. Now, this radio here has, again, it's not these standardized All-American 5 style tubes or octals or anything like that. These are old glass tubes, and whenever you see a tube that has this little dip on the side of the bulb, these are known as shoulder type tubes or ST style tubes. Now, before Rogers had, really gotten known for their spray shields, they used to put a shield on the outside of these glass tubes known as a goat shield, like Billy Goat, goat shields. And that's what these are commonly known as. Now, this tube here is underneath this metal shield so that this tube does not see that tube and this tube does not see this tube. They shield the tubes so that they don't oscillate with one another. So for example, if you have a guitar amplifier and you plug a microphone into that guitar amplifier and you bring the microphone close to the speaker, so you bring its own microphone close to the speaker, what's going to happen? Well, it's going to start to squeal and make all sorts of noise. And that's because it's oscillating. What's happening is it's causing feedback. It's squealing in there. Well, tubes do the same thing when they see each other. They'll start to squeal, especially if they're, a high gain stage. So the way to stop that is to stop one tube from seeing the other tube. And by doing that, you shield the tube. Okay? Now, when this tube would oscillate with this tube, it's much higher than the audio frequencies that you would normally hear. So if you put a microphone close to a speaker on a guitar amp, it's going to squeal and it's going to be audible. So you can squeal and it's really loud, right? You can hear that. Well, this is going to be oscillating at a much higher frequency. So you're not going to hear it or anything, but what's going to end up happening is these tubes are just going to cause all sorts of problems with one another because they're feeding back, but at a much higher, maybe at an RF frequency or something like that. So in order to stop that, they put metal shields on the tube to isolate the stages a little bit better. Now, as time went on into the 1940s, they actually put metal shields on the tubes themselves, and we'll take a look at those particular types of tubes down the road here in the future when we service another radio that has those metal tubes in it. I'll explain that then. So these tube shields here have a little cap on the top, which also shields the grid cap. So the signal goes in the top of the tube here, and then it comes out on the bottom side of the chassis. And that's with this tube and this tube here. And you can see here we also have a grid cap on the top of that tube there. Now, one thing you have to be very, very careful with is if you're working on something like a transmitter or an old transceiver, say like a Yaesu, a Kenwood, EF Johnson, Heathkit, whatever like that, not all of the caps on the top side of the tube are grid caps. Some of them are the anode caps. So if you're working on a transmitter, some caps on the top of these tubes can have between, say, 700 all the way to 4,000 volts on them. And the caps are exposed inside these transmitters and things like that. So you need to know your vacuum tubes. So say there was a large ham radio amplifier, okay, and it had a big tube inside it, and there's a cap on the top of the tube. That is not a grid cap. That is a very high voltage point. A high voltage point that would kill you instantly if you were to touch it. So these are all things to remember. Now, in this particular radio, these are all grid caps, so there's just signal coming in here. There's no, crazy high voltage unless something really goes wrong inside the radio. There's no high voltage really present on them. But again, you always have to be careful, especially with any exposed connections inside of an old radio like this, because you don't know what anybody's done. Somebody could have been inside this thing and butchered it up really bad, and who knows what's happening. Again, we're going to discover all this together. So I'm going to go over all of that safety stuff and show you how to recognize tubes that have plate caps and grid caps and how to know the difference. We'll do all that here in the near future. I have a bunch of really big transmitters that we're all going to go through together, and we'll get them running as well. So that should be a lot of fun down the road here. So really what we need to do is attach this line cord to an isolation transformer and current limited variac supply, and I'm going to do that. What I'm going to do is I'm going to troubleshoot this thing just the way it sits right here. We'll see what we can learn by just troubleshooting it just like this. So I'll get everything hooked up and I'll explain that here in just a moment. The radio receiver is attached to an isolation transformer and current limited variac supply. So basically what that does is it limits the amount of current that's supplied to this radio receiver. So if this radio receiver, say, tries to draw a little bit too much current, that device will limit that so the radio cannot be damaged. For example, say there's a shorted filter capacitor or something in here. I don't want that to destroy the rectifier tube. So that supply will limit the amount of current that's available to this radio receiver. It's also attached to an isolation transformer. The isolation transformer eliminates the chance of this chassis being attached to the AC line. So basically it's like a one-to-one transformer that isolates the AC line from the chassis. A very, very important thing to have for safety whenever you're working on any type of radio where one side of the AC line could be attached to the chassis. I've talked about the dangers of this in other videos. I'll quickly go over this again. Say this didn't have a polarized line cord and you plugged this in so that the chassis was hot. If you took an oscilloscope probe and attached the common from a normal oscilloscope probe right to the chassis, it would blow the oscilloscope probe right off. You would get a huge flash. A lot of the times it damages the oscilloscope, things like that. So isolation transformers are very, very important to have whenever a radio like this is on the service bench. Extremely important to remember. All right, so what I'm going to do is I'm just going to turn this thing on and I'll let it warm up and we'll see if there's any sound coming out of this. I have this attached to an antenna right here. This red lead runs out to an antenna and we'll see if there's any sound or anything that comes on. So that's a good sign. The dial light comes on in there. And the bulbs on the dim bulb tester did light up just a little bit when I turned that on. So we'll give it just a moment here to warm up. Since this has a ballast tube in here, it'll take just a little bit longer for this to warm up. And not only that, the line is reduced, so the line voltage is reduced down just a little bit, as well as being current limited, just to be really safe with this thing. Again, I don't want to damage this rectifier tube and have to go and hunt one down and find another one to replace it because, you know, I kind of plugged the thing right in and tried it. So very dangerous thing to do, again, with something like this, is you never ever want to plug something like this in directly into the wall without it being properly serviced because, again, if anything is wrong on the underside of the chassis, you could ruin a very expensive tube, i.e. the rectifier here. So it's glowing. I can see it glowing. What I'll do is I'll just zoom on into that. Bear with me here. All right, see the filaments glowing in the top there? So it's on. And it's normal not to really see any type of a glow in a ballast tube, but the rest of the tubes, the cathodes, would be glowing in them as well. So I'll just back the lens out here a little bit. Right to about there, and I'll give it some volume. And the thing is just silent. So I'll move the dial around. Absolutely nothing. Try the band switch. It's not even humming or anything. It's just so quiet. Dead silent. So at this point, I don't know if there's any B plus or anything happening because I don't have this out of the cabinet and I'm not using a voltmeter at this point. So this has a field coil speaker in it, basically an electromagnet speaker. So this is before permanent magnet speakers were around. They actually had a coil wrapped around it, and that would magnetize the speaker. Now, if there's no B+, there'll be no magnetism. There will be no, B+ is the positive that comes out of here, by the way. So there'll be no magnetism on the speaker or anything like that. And it's sitting silent. Like, I mean, there is just no life here whatsoever. So what I'll do is I will grab the Carlson Superprobe and we'll just sweep around in here just with it just like this, and we'll see if there's any signals or any oscillator or anything's happening with the thing just in the case, just to get an idea real quick. And we'll see if there's any hiding life happening inside here that we can't tell. Boy, that's just dead silent. I have the Carlson Superprobe on the bench here, so this is just an amplifier. The probe itself has got a bunch of circuitry inside it, and this is just an external speaker, that's all it is. So there's some batteries in here, and this is the power for this probe as well. Now, I released this on YouTube quite a while back. If you look down my videos list, you'll see Carlson Superprobe, and you can see the schematics and how this thing is built and everything like that if you want to put one of these things together for yourself. If you're really serious and you want to build the actual circuit boards for the amplifier and the parts list and everything is already sized and everything, that's all up on Patreon. So all of the layouts are already sized. You can just print off your own circuit boards and, you know, make an exact copy of this pretty much if you'd like. In fact, many people have, and they've shared their projects up there. So this is on right now. Everything is on. And what I want to do first of all is see if there's any B plus or anything happening in here. And the easiest way to do that is to use this thing to see if the oscillator is running. If the oscillator is running, this little LED on the back side of the probe will light up really bright when I put this close to the oscillator. So I'll turn this thing on, like so. I have the gain turned down. There's a different switch setting for RF and audio on here as well. So I'll attach this here, and I'll just slide this in here and see if the oscillator is running. So the oscillator is running inside this thing. That means that there is B+. There is DC flowing in here right now. There's just nothing's coming out of the speaker, which is kind of interesting. So the oscillator is working, which means that we might actually be receiving radio signals. So the first thing I want to do is make sure my actual antenna is receiving something. So this thing is so sensitive that it will just, in fact, I can just leave it on this side and just go close to the antenna wire. So I'll turn this up really sensitive. And so you can hear it's receiving stuff on the antenna. So no problems there. So just holding this close to the antenna wire is all you need to do to see if the antenna is actually receiving anything. You can hear Morse code in there and everything. So the next thing I want to do is I want to bring this close to the grid cap of the modulator oscillator, sometimes known as a converter or mixer or whatever. And I want to see if I can hear any radio stations with this thing. So I'll put this here. And I do. So I'll give this a bit more audio. And I'll just tune the dial around. So the whole band is active. So what that's telling us so far now, what that's telling us is that the signal is getting into here through the antenna coil and into this, and it's actually tuning it. So we've verified a whole bunch of things just by doing this. First, we know there's B+ here, so the filter capacitors must be doing some form of work, because I don't really hear all that much hum or anything present. I'm hearing radio stations, which means the signal's getting in from the antenna into here, and this is tuning it. So the next thing I want to do is I want to see if that signal is getting right into the IF tube. All right, so there'll probably be just a little bit of signal reduction here. So let's see if we can hear anything here. Just listen to the grid lead here. I'll move this around. And you can see the LED kind of get a little bit brighter when I hit an actual radio station. It's not incredibly strong. See if you can hear anything like this. No, that's more of an audio setting. So there is signal there. Can you hear that? Those are about the strongest signals, I think, right up about this end here. So you can see it get bright when I get onto the station. So there is signal getting through the IF transformer into that first IF tube right here, and then that would be amplified and then run out to the detector. Now I don't think we're going to hear anything at the detector. Let's find out. Oops, ground clip popped off there. I didn't think so, because the signal is pretty faint at this point right here as well. So we already know that the thing is trying to work, just nothing's getting out of the speaker. So most likely the problem is dwelling in this area right here, because it's working up to this point. It got a little bit weaker here and nothing here. So I would say IF audio section somewhere in here is a problem. Now, since the speaker is dead silent, it's that, you know, raises concern of the actual audio section itself. So the only thing to do now is to remove this thing, and let's really get into it. Let's, you know, probe around with this thing and see where the signal goes missing. And then we'll also take a look with an oscilloscope as well. Show you how to do that with an oscilloscope and find everything out. Now, don't get me wrong, finding the signals in here and locating this stuff with an oscilloscope at this point wouldn't be possible. It's not as sensitive as this device right here. This device is actually listening to the antenna line, as you heard, so we could hear just random signals on the antenna line, right? So if I go back to the antenna here, you'll hear this. So you can actually hear signals coming in on the antenna line with this thing. That's how incredibly sensitive this thing is, right? Now it's so sensitive, it's lit right up because of the sensitivity here, right? So an oscilloscope is good for, you know, troubleshooting if you actually want to tie into points or get very close and couple in. Like if you bring the probe very close to a high signal point, sometimes it'll couple into the oscilloscope probe. So that works fine for that. So, you know, two different, you know, tools for the job, but I'll show you the difference between the two here and we'll get this thing running. It looks like it's just about there, honestly. I mean, you know, there's, you know, radio stations in here, you know. So we're well on our way at this point already. So it's working at this point, just not the radio. It's needing this thing to make noise out of this speaker right here. The radio was unplugged from the supply, and it's been sitting for a while to let the tubes cool down. Getting inside this radio looks relatively easy. So the first thing we need to do is take the knobs off of the radio because the chassis comes in from the back side. So I'll just pull that one off. Oh, those come off really easy. I'm really lucky these things didn't get lost. They almost feel like they could just fall right off. And then the next thing to do is to remove the feet. The feet have little screws right in the center of them. So I'll remove these feet and this thing should probably just come right out. So I'll take the two bottom ones out first. You can already feel the chassis letting off there. So what I'll do is I'll just put my hand on the back side of the chassis so it doesn't want to fall right out. And this one right here. And I think we are in. Look at that mess on the bottom side. That's quite the mixture of old and newer components. Put that over there on the floor behind me, the case. So I already see a mixture of different parts and lots of original parts. So very few parts have been changed in this thing. Looks like this, and this have been changed in the line cord so far. And I think that's it. So these are the filter capacitors. This is a filter and a filter here. Somebody's put in these orange dip style capacitors. And lots of original parts. Wow. Okay, what I'm going to do is reposition the camera, zoom on this, and we'll take a closer look. In fact, you know what? Let's take a closer look at the radio first. Look at that speaker. That looks like it's just pristine. I'll move it to make sure it's not grinding. No grinding, no anything. That's nice. Nice and fluid. No problems there. This looks like the factory filter can over here. And it may actually still even be hooked up. Who knows? Here are the tubes. That. Let's say 25L6. That's a nice looking little tube there. Nice compact little chassis, nice and solid. Audio transformer, field coil speaker. You can see the electromagnet wound around the speaker here. Lots of winds of wire there. And the filter can right there is poking up through the top. Well, that's really quite a large filter can. And just lots of original looking capacitors, coils and such. Well, it's nice to know that it hasn't been tampered with all that much, aside from a line cord and maybe a few capacitors. The majority of this looks original, so this will be a lot of fun to see how many parts we actually need to replace to make this thing make noise. Should be a lot of fun. All right, I'll move that camera, and I'll be right back. Here's a closer look at the bottom side of the chassis, and immediately I can see that they've disconnected one of the filter capacitors on the top side of the chassis here, so that red lead's got some tape on it. They've installed some other capacitors here, so these may have been installed at different times. This one here is older than this one right here, so the underside of the chassis may have been visited a bunch of times, including the line cord. So the orange dip is here, but all the rest of the capacitors and resistors, these are known as dog bone style resistors, are all looking pretty factory. So this here has the factory coding on it, all these capacitors. So you can see C10.4, C10.5, and if we look at the schematic, you can see 10.5, 10.5, 10.4. So those are definitely all factory components, which is kind of nice. So there's not a whole lot of tampering that's gone on the underside here, so it'll definitely give us something neat to troubleshoot. So looking at the schematic here, we can see this ballast here, and as you can see, it's in line with the filaments of all these tubes. So again, if one of these filaments was to open up, right, all of them would not glow. They've put the dial lamp across the 15 ohm portion of the ballast. There's 130 ohms worth of resistance right here. So this is just in line with the actual filaments of the vacuum tubes. So another thing that's really hard on these ballast tubes is if you ever find one of these tubes on the top side of the chassis, and you'll notice that most of the tubes, I'll just turn this back over, most of the tubes have this kind of a chromy look inside. So some of them have a chrome getter. You can see this is the getter on the top of this one here. It's kind of a chrome look on the inside. If you ever see that that's gone a powder white color, you definitely don't want to be plugging this thing in, because what's happened is that tube has come to air. So the seal on the tube has broken, and it's really hard on the other tubes and the other components if that has come to air. So you definitely don't want to be powering anything up if you see any tubes with a white powdery coating inside. So I was talking earlier about the safety of this particular radio, and as you can see, what they do is they have one portion of the AC line through a switch directly to the chassis. Now, this ground is the chassis. There are no chassis symbols on here. And if we look what comes off the switch right here, I don't know if you can see that, this wire right here goes directly right over here and solders directly to the chassis right here. Right there, you can see that. So one portion of the AC line is definitely connected to this chassis, and that's most likely the reason that they put this polarized plug on. But here's the thing. So if you were to make this, the chassis actually positive, it would, or hot, I should say, it would make this thing very unsafe. So you would, you know, if just say that this was the hot side and this was the neutral side, all right? If this was the hot side, you'd be running the hot side directly to the chassis, but the switch would be in the hot side. So when you open the switch, the hot would be broken and everything would be okay that way. But you can see that the neutral is intended to go to this side. So this radio will accept either AC or DC. So you can feed this with direct current as well. So if you fed this with direct current and you made this positive and this negative, it wouldn't work because the diodes or this rectifier here would be backwards, right? So it wouldn't do its job. So it's intended that this side here is positive, or the hot side, and this here is the negative and neutral side. So what ends up happening here is if you open the switch here, all right, to the ground on this side here, and this side is hot and this side is neutral, you're opening the neutral line right to the chassis. Well, what happens is you have this which goes directly through all of these tubes. So if this is hot, the hot isn't broken, right? Because we have the neutral side here with the switch in it that's broken here. So if this is hot, you can see that if you break this connection to the chassis, the entire chassis will float as being hot, right? Because only the hot connection will be connected. So it will go through all of these resistors and the tubes right to the chassis, which makes this a dangerous situation. So in the event that this was to be restored, what you would want to do in a case like this is make the neutral solid to the chassis so that it's safe, and use an indexed plug or a polarized plug so that the neutral is always connected to the chassis, and then move the switch to the hot side. And in most cases, I'll even add a fuse in a case like this. So I'll put an absolute value fuse in here. So this here would remain solid to the chassis, and the switch would move up to this side so the hot gets broken. That would make this a lot safer than it is. So kind of an interesting thing. You open the switch and the radio, or you turn the radio off and the radio becomes more dangerous in this situation right here, which is kind of interesting. So one of the things that has to be fixed. So over here we can see the field on the speaker. This is an interesting field connection. It takes the B plus through the field directly to ground. So this is a 3,000 ohm field right here, and that's a load for this rectifier for sure. You can see that they've taken both plates and both diodes and attached them in parallel. So there's obviously going to be more current passage through this diode, less drop across the diode, and it just goes right to this field directly to ground. In a lot of old radios, what they do is they actually run the B plus through the field on the speaker, and then the rest of the radio draws current through that field, and it magnetizes the speaker. In this case, the field connection itself is basically just a coil right to ground. Kind of an interesting setup. And you can see here, they have this 400 ohm. You can see that we have a choke right here, and this runs through this choke. So we have two capacitors right here, one on each side, and then it runs up and feeds the rest of everything else. So if we look here, we can see we have an audio output transformer, and we can see we have a choke down on the bottom. 40.16 is its part number. So let's see if that is the same on the parts list. There it is, 40.16. So this is the choke. So all in all, when you really look at this radio, this is a very well-built radio. Most radios of this era, they won't be doing this. They won't be doing this. Again, they'll be running things through, the current through the field and using the field itself as somewhat of a filter. So put it this way, there's a lot of iron in this radio receiver. It would have cost a lot of money to put this together. And that's why these fatter radios were more expensive than the rest back then. So we have a choke here to, again, get rid of some of the hum. So we have a filter on this side, we have a choke, and then it runs off to this side. Through the choke, it goes up here into the audio transformer, and then of course it feeds all the B plus to all the tubes right here. So the most common problem in a radio receiver like this, after it's been sitting for an incredible amount of time, is these capacitors here both go bad, one or each or both, and they'll either open or they'll short. And if either one of these capacitors goes bad, what it does is it takes this rectifier tube out. It'll destroy the 25Z5. So what it'll do is it'll blow the bonding wires off the cathodes. Now, if I can take this tube out here, maybe I can show you what the bonding wires are inside the tube. So let's take that out again. Let's see if I can see the bonding wires. I can see the filaments on the bottom, so I'll try and zoom on into this a little bit here. See if we can see the bonding wires. Okay, you see that little strip right there that's running off? I'll try and get my little tool right here. You see that little strip that's running off right over to there? And let's see if I can point out the other one. See this one here with a little hook in it? Kind of hooks up and then runs over here? Those are the bonding wires to the cathodes. And if one of those filter capacitors are bad, these things act like little fuses. They just blow right off inside the tube, and then the tube doesn't work anymore. It'll still glow. The tube itself, the filaments that we looked at earlier, will still operate, but it won't work anymore because it's just, you've actually destroyed portion of the circuit. It blows this portion right here blows these little, these are the cathodes here, so it blows a little bonding wire off. The part from the bottom portion of the C to the outer portion of the bulb here, it blows those little bonding wires off. So there's no connection from the cathode itself to this line right here. Again, it'll still glow because the filaments are on a separate circuit. It's just that the rectifier won't do anything anymore. So I'll just zoom on out here. It's all back into view again. So again, these capacitors are what causes that problem all the time. Now, when capacitors like this short out, this tube here will draw heavy current. Usually these capacitors end up going bad, and what they do is they pass the plate voltage from this stage into this stage, and basically what that does is it turns this tube on really, really heavy. This tube draws a lot of current, and sometimes what it'll do is it'll open the audio transformer or cause other damage here. So these coupling capacitors are always a troubled spot. And we can see these decoupling capacitors here between the two resistors, right? You can see these capacitors here and here and here, and we see all these capacitors. All those capacitors are real sore spots in this. You'll notice on the antenna circuit here, we have a capacitor that's in line with this antenna coil, right? This capacitor here is in line with the antenna coil to the actual antenna itself. If this capacitor here goes bad, and way back when, if you had a non-polarized plug and you had it plugged in the wrong way and the chassis was hot, there's a really good chance that you'll destroy this antenna coil if it's attached to something outside, you know, or if there's any leakage from your antenna to ground. Some people had some pretty goofy ideas way back when in order, you know, to make the antenna work. People would do things like, you know, ground these things to their radiators and sometimes even make the radiator in their house the antenna. Real goofy things like that. And what it would do is it would absolutely annihilate this coil right here on the antenna coil. So this is a coil here that kind of sticks out above the rest. You see that one right there? Just end up blowing that coil right off. So they open up. So it's always important to make sure that this capacitor is good. I usually replace this capacitor here with a safety capacitor as well, so an XY rated cap, just to be even more safe. So this is a real sore spot. I've taken some Hammerland radios apart, and the coil on so many of the bands has just been blown up. So what happens is they try and listen to, say, the 80 meter band, and they move the band switch to 80 meters, and then boom, it blows the coil off. And they move it to, say, 40 meters, and then it takes out the 40 meter coil, and they've moved this along. So a lot of people have done some pretty goofy things with their antenna systems. So now what I usually do is put a capacitor in line with the antenna connection to the antenna coil, and if something ever does go wrong, it protects these coils, because these things are really hard to get now. And if something like this was open, it would have to be rewound in order to make the antenna circuit in this radio receiver perform like it should. These are the IF transformers that you saw on the upper portion of the chassis right here. This is the IF tube right here in the center. So it's the IF tube right in the center. So they call this a converter in this one here. Sometimes they're called oscillators, modulators, mixers. In this case, it's a converter. Just depends on what the manufacturer wants to call it. So there's an oscillator in here that will oscillate. Let's see, what is the IF of this radio receiver? Oh, here it is. IF peak equals 456 kilocycles. So the oscillator in here will always be 456 kCs above what you're listening. That's how it works. And then these transformers are tuned to 456 kCs or kilocycles, and then what you're listening to, or what the antenna is receiving, is present at this point right here. So what happens is say we wanted to listen to 1000 AM, all right? So 1 megacycle, 1000 kilocycles, however you want to call that. The oscillator here, if the IF chain is tuned correctly, so these two transformers here, if they're tuned correctly, the oscillator would be sitting at 1.456 megacycles in order to be receiving 1000 AM. So that's how this works. Now, I explain a little bit more the way the IF section works in some of my other videos. I have an Eddystone. Is it an Eddystone? No, it is a Echophone. I have an Echophone video, EC1 video, where I really get into explaining how this works. So if you want to understand more of how the IF and the converter and oscillator work in a radio receiver, that's a really good video. I go into detail right there. So again, this is always, when you're tuning the dial, the oscillator is always 456 kilocycles above what you're listening to. So this is oscillating all the time. And you hear those stories about those trucks running around way back in the day with loops on the top to see who had radios. Well, this is what they would listen to. They would listen to this oscillator tube here, because a lot of the times the oscillator or converter or mixer, whatever you want to call it, inside one of these radios is strong enough that it will backfeed the signal out of the antenna. So your antenna is actually transmitting the same time it's receiving. So again, this is the reason that they used to have a thing called pre-selectors, and in some cases they'd even put one RF stage in front of this to isolate the oscillator from the antenna just by one more stage. That's another story altogether. So way back in the day, that's what happened. So they could even tell what, depending if they, could make the correct guess. This is close enough to 455, so it's 456. They could even make a guess at, what frequency you're listening to if they could get close enough to your antenna, and pick up the oscillator, right? Again, if they're receiving you at 1456, they know you're listening to 1 megacycle. Kind of interesting. Again, the need for pre-selectors and one RF amplifier in the front end of most of these old receivers, and that was quite common in military receivers. So, what we need to do is we need to see where this signal is going missing. We see that the converter is working, so the oscillator portion of this converter, this is doing two things. It's an oscillator and it's a mixer. That's what this one little tube does here. It's doing two things. So, we know that this thing is oscillating because we saw that with the Carlson Superprobe. So we want to follow the signal all the way down and see where the signal is going missing. And we also want to see if this actual field is working, because the radio is really quiet. And we can do that very easily, even without a voltmeter, just by touching a piece of metal to the center portion of the speaker right here. And we can see if this is magnetized or not. And that'll tell us whether that field coil is actually working. So what I'll do is I'll get some test equipment hooked up, and let's find out where the problem is in this radio receiver. I have the radio attached to my isolation transformer and current limited variac supply, and it's on right now. So I have to warn you, working on something like this is dangerous, especially if you don't know what you're doing, because there's high voltage present all over the place in these radios, and of course the risk of the chassis itself being hot. Again, this is on an isolation transformer, so this is much safer to work on, but it still has lots of dangers. So if you're following along, you're doing so at your own risk. So what I want to do is I want to look for the signals in here. Now that I'm on the underside of the chassis, I can get the non-contact probe a little bit closer to some of the pins, and we can see where the signals are. So first of all, again, we can look to see if we can hear a signal on the antenna. I'll turn on the Superprobe here. So we'll listen to the antenna. So we can hear that there's a signal at the antenna. So I can go over to the antenna coil itself. So I can tell that the antenna coil is working. So what I'll do now is I'll go close to the oscillator, and I should see the green LED come on nice and bright. See how it gets quiet and it gets bright? It's a sign that the oscillator is working. So let's go close to the IF tube and see if we're receiving any radio. No problems there. We can see that we have signal on the IF tube. I can even tune this. So now let's go over towards the detector tube, which is this tube right here. So if we look at the schematic, I want to go close to the detector plates. You can see that there's two plates tied together inside here. And if we look here, we can see that there's two leads tied together right here. And that is the detector plates. So I'll just move this over to this side over here. Let's clip this on here like so. Let's go towards those detector plates and see if the signal is getting, just grab the schematic here again, see if the signal is getting all the way over to this point right here. So let's move that out of the way. So turn this back up. No problems. In fact, it's very strong. Probably turn it here.
5 to 7, here on.
You hear that?
Wesley is
no problems.
a truck driver.
Lots of signal over there.
Really bad. I caught a few letters in the mail.
So lots of signal present at the detector plates over there. Yet we still have nothing here. I can turn the volume all the way to its max, which it actually is right now. And this thing is just sitting dead silent. So let's turn that off. So what I want to do is I want to actually see if this is magnetized, if the actual field is magnetized, because if this thing isn't magnetic, you know, it's not going to be working. Oh, you can see it's definitely magnetic. So it's sticking to it, so there's enough magnetism there for the speaker to work. Yet, there is nothing. Now, I told you that I'd show you how this works with other equipment as well. We can see if the oscillator is working. Now, I'll show you with this one here quickly again. So I'll put this back on the chassis here. And this is the oscillator coil up here. So oscillator and antenna coil. So I'll turn this back up. And you can see here, if I get close to the oscillator coil, you can see the little green LED coming on and it gets quiet. So we can determine that the oscillator is working just like that. I turn this down. Okay, so if I turn that down, that's with the sensitivity of the probe turned down, so that way it's a little bit more positive. Very easily we can tell that the oscillator is working with the Superprobe. Now we can also do that with an oscilloscope. And what I'll do is I'll go grab a scope and I'll show you how that works, and a very easy way to check the oscillator with an oscilloscope without really making any connection. Here's an example of how to use an oscilloscope to see if the oscillator is operating. It's really quite simple. The common lead of the oscilloscope probe attaches to the chassis, and you can take the probe itself and insert it right into the oscillator coil, just like that. And look what happens. We can see that the oscillator is operating. I can give it just a little bit more vertical sensitivity here. So the oscillator is operating right now at 1.96 megahertz. So keep in mind that the radio is receiving 456 kilohertz lower than this right now. So again, the oscillator is always 456 kilohertz higher than what you're listening to. And that's how easy it is to see if the oscillator is operating. Now keep in mind that if you take an oscilloscope probe like this and you put it inside of an oscillator coil like this, it's going to drag the circuit. This is a really high impedance circuit, so it'll drag the oscillator off frequency, but it'll still give you an idea if the oscillator is operating. And we can definitely see that it is operating. We just have absolutely no audio coming out of this radio receiver. That seems to be the issue. So let's find out why we have no audio. The radio is just sitting silent, and the speaker itself is magnetized, so the field is working. So there's obviously something wrong in the audio section over here, and that's what we're going to look for now. By using the Carlson Superprobe, we found that the signal is getting all the way to the detector plates, but the whole audio section is quiet. So this tube here is a detector and audio amplifier. So if we take a look at the schematic here, the signal that we listen to is getting all the way to these plates right here. So this is the detector portion of this tube, and the triode that you see in here is the audio amplifier portion. The next thing I want to do is check the plate voltage on the 6Q7 and see what that's at. And then I also want to check the plate voltage on the 25L6 here. So the plates in both of these tubes are pin 3. Consequently, the screen grid in this tube is pin 4, and the control grid, which is where the signal goes into, is pin 5. And the cathode in this tube is pin 8. And we're going to be taking a look at all of that stuff here. So I'm going to check out the plate voltage here on the 6Q7, which is pin 3. So what I want to do is put this to the DC meter, and I'm going to go over here. Now, pin 3, if we look at the index here, we always count clockwise. So this is the index, this is pin 1, pin 2, and pin 3. So this is where I want to check the DC voltage. And there's 12.2 volts on the plate, which is extremely low. All right, so now I want to go and check the plate voltage of the audio output tube. Again, this is the index over here. So we have pin 1, pin 2, and pin 3. It's very low on this, 10.6. Let's take a look at the screen voltage. 17 volts. So there's actually quite a bit of a drop across that audio transformer. Let's take a look at that. So there's quite a bit of drop even at that low voltage across this audio transformer here, which is very interesting. So, again, pin 3, okay, right here, we have 10.6 volts, and then if we go over to the screen is high, so this here is the screen, so we're getting a drop across this audio transformer, quite a drop across that. So let's check the voltage at the cathode of this tube here. So the cathode again is pin 8. So that's this one right down here. This last pin right before the index. Wow, that's incredibly high on the cathode for a plate voltage of 10 volts. So that would either be a shorted tube or something. So this is the cathode. And this here is the plate. There's pretty much no difference between the two. So now if we look at the cathode right here and we look at the plate, what's connecting these two? We have this capacitor right here, which is connecting these two. So again, we look here, the plate, all right, 10.61, which is at this point right here. And if we go to the cathode, which is pin 8, we can get this down in here. There it is. Basically the same, 10.59, 10.6. This nice polished cap here is keeping me from getting my probe into that area down there. So there's a really good chance that this capacitor here is shorted. And that capacitor is running from the plate, which is here, to the cathode. And that's this cap right here. So why don't we try and open it and see what happens? I'll just clip it open. Wow.
Frequencies world. You want
Well, I would definitely say that that is the problem. Now that the capacitor is removed and the radio is operating, let's take a look at the plate voltages. So this is the plate voltage on the output tube, and this is with the current limited supply in line right now. So you can see there's quite a jump from about 10 volts all the way up to 51. Let's take a look at the plate of the amplifier tube. quite a bit higher, 34. Now what I'm going to do is I am going to up the supply here to its max right there. And as you can see, the sensitivity is picking up. So if I move the band switch, that's a little bit better. So make things nice and quiet so we can test this out. 95 volts on the plate of the audio tube, the audio output tube, and almost 50 volts on the plate of the audio amplifier, and that is looking a lot better. So this capacitor here is acting as a bit of a snubber in the circuit here. So get this here. So this is acting as a little bit of a snubber, and it also knocks out some of the high frequencies. So it tones down the sound of the receiver just a little bit. So this capacitor here should be replaced with the same value, and it looks like it says it's 0.03 on here. In order to, bring this radio, bring the tone of the receiver back down again, it'll affect the tone just a little bit. So let's see what's actually wrong with this capacitor here. What I'll do is I'll shut the radio off. And let's go over here to the ohms meter. Actually, let's go to continuity because I've got a really good feeling that this is shorted. So I'll go enter. And I will put one lead over here on this end of the cap, and let's test this end. That capacitor is a dead short. So that's definitely the problem, and the radio seems to be working just fine without this cap. So this will definitely need to get replaced. Now, for right now, it's not one of those crucial components. I can just take this thing right out of here. I'll turn the, there's quite a nice little burn on that side as well. That might be the reason. You see that right here? Quite a little bit of a burn there. That'd be one of the reasons why this thing actually shorted, or the short inside the cap might have actually caused that burn in the paper right there. You can see it's melted the wax away from that spot. Kind of interesting. That was hidden on the other side of the capacitor. So what I'll do is I'll just turn this back on right now. I'm just going to turn it on first in current limit mode. And I'll let everything warm up here. I want to be nice and easy on this because this still has all the original caps in it at this point. Let's move this out of the way. Get this out of the way. Just shut this off. And we can cruise around the dial a little bit and just see how well this works at full line voltage. Alright, so here we go. Turn this back over to here. And here's a little bit noisy. And I'll turn this up to full line. You can hear how sensitive that is. It's not on a frequency right now. And that's as low, right here. About as low as the volume goes at this point. So I'll just leave the volume right down.
.com today.
It's actually working extremely well for all of these other original components. I wonder if the shortwave band works. Definitely tell that switches and stuff need to be cleaned on here. It's very temperamental. Some CW. That must be right at the top end of the broadcast band again. Oh, there is the time signal. Oh, wrong way. That's the WWV. Wow. So it's working very well, even on the shortwave bands. So I'll just shut this off. So the whole radio is working. Just that one capacitor stopped this thing from working. And that really is the problem with leaving all these old components in here, is because really it's basically just guess when the next one's going to go. Pretty much spin the wheel and, you know, take your best guess at this point. So there's a lot of other wax capacitors in here that could fail at any time, and some of these are looking like they are just about ready to go. You can see, looking at this one down here, the line cord right now is disconnected, by the way. You can take a look down in here, right? Some sort of a black stuff, it looks like it's almost coming out of the capacitor there. So in order to make this radio dependable and operate properly again, it's going to require an entire restoration. So basically all the capacitors that you see on the bottom end will need to be removed, including these capacitors here, this capacitor here, you know, and all the capacitors in this section here, this waxy and this waxy up here, they all need to get replaced. The ones that can stay are, move the chassis over, you can see that there's these mica capacitors here. So I'm just going to move the focus over here so that way we can see this. So like these capacitors here are usually okay. So this one here can stay, and the capacitors that are like that. But anything that's a waxy, you know, like that waxy down in there, this one up here, all of these have to go, as in any of my standard restorations. So these dog bone resistors all look to be in really good condition, and at the time of restoration, if this thing is actually going to get restored, I'll go about replacing all the capacitors at that time and testing all the resistors, and we'll do that all together. So that's all it took to get this working. We found our way all the way to the problem and eliminated the problem, and the radio came back to life. So do you think we should actually go through and completely restore this radio and make it work like the day it rolled off the factory floor? You can let me know in the comments below. And if there's enough of you that want to see this thing get restored, we'll go through the entire process together and bring this thing back to life. Make it work the way it did way back in 1937. Thanks for stopping by the lab today. I hope you enjoyed this diagnosis and troubleshooting procedure. If you are enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the very near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. The official Mr. Carlson's Lab 2020 calendar has been released, and it's photograph quality. Just below the video's description is a Show More tab written in capitals. If you click on that Show More tab, it'll expose the link. You can click on the link and it'll take you right to where the calendar is. You can flip through the pages and check out the entire calendar. Lots of really nice pictures in there from many of the projects that have been on the bench here. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're definitely going to want to check out my ongoing electronics course on Patreon. I'm also sharing many of my personal electronic designs there as well. The circuit board designs and all sorts of information for the Superprobe that you saw here on the bench is up there, and many other pieces of custom test equipment to make your troubleshooting procedures all that much easier. Definitely check it out. I'll put the link just below the video's description as well under the Show More tab, so I'll put that just below the link to the calendar, and I'll also pin that link at the top of the comments section so it's nice and easy to find. All right, until next time, take care. Bye for now.